Bem, boa tarde a todos. Meu nome é Hugo Sandin, eu sou da Escola de Engenharia de Lorena, trabalho no Departamento de Engenharia e Materiais, e hoje eu tenho o prazer de trazer o professor Daniel Abou-Ras. Daniel é formado em Física em 2005 pela ETH Zurich. Um ano depois, conseguiu uma posição no Instituto Helmholtz, no Centro Helmholtz, em Berlim, na área de materiais e energia. Conseguiu a sua habilitação, que equivale à nossa livre docência aqui no Brasil, em 2015. E, por consequência, ele é privatdocente. Então, ele não é um professor universitário, mas ele ministra aulas em universidade. E ele atua em duas universidades, a Technische Universität Berlim e também na Humboldt Universität. Daniel tem hoje 50 anos. Ele tem um background no Brasil, a esposa dele é brasileira. E atua lá em Berlim há muitos anos, com ênfase em caracterização microestrutural de materiais para células fotovoltaicas. Então, conversamos com o professor Alain, o professor Renato, o Germano, e hoje ele está aqui para apresentar, o título da apresentação dele está aqui. À vontade, então. Muito obrigado.
Muito obrigado também, Hugo, para a introdução e também muito obrigado para o convite, né, aqui na USP. Faz 17 anos que visitei o campus, mas bom, eu não lembro exatamente todos os detalhes, porque eu visitei um laboratório só e bom, eu espero que a gente pode entrar em contato, discutir um pouco sobre possibilidade de colaborações. Muito obrigado já para apresentar os laboratórios e o trabalho. For the presentation, I will switch to English because I speak Portuguese, but it will not be sufficient to give this talk in Portuguese. So please excuse this detail. So at the Helmholtz Center Berlin actually is a research facility in Berlin that actually accommodates also the Berlin synchrotron source, BESSY, BESSY 2. And so basically, most of my colleagues, they are dealing with the operation of the synchrotron source as well as with various experiments operated at the beamlines. I myself, I'm a group leader at the Helmholtz Center Berlin for electron microscopy. So I started actually my career in transmission electron microscopy, and I somehow added scanning electron microscopy then, and basically I have used these techniques over the years to analyze various materials, but mostly solar cells. So I have already worked with superconductors, with various metal alloys, with energy materials for solar fuel production, for batteries. That's a very intensively studied field at the moment at our center. So yeah, I'm familiar with a lot of material systems. Okay, and before I start my talk, I would like to acknowledge my colleagues in my group. Basically, are not in my group anymore. So most of them, they're my students and ex-students, but they contributed to all kinds of results that I will show you in the next minutes. And we have also a really great technical staff, mainly operating the specimen preparation lab, because for us this is the bottom, the fundament actually. Whenever the specimen is not well prepared, we can't really get good results at the microscope, right? So we are really grateful to have a good lab and also good staff. And actually all of the results that I will show you are a result of a collaboration with various institutions, but also with companies. So as an outline, very brief outline, I will tell you a little bit about correlative electron microscopy, but also microscopy in general, because basically what I have concentrated on is to combine various electron microscopy techniques, but also scanning probe or Raman microscopy with one another on identical positions, right? Just in order to have a good means to have structure property relationships, right, of specific materials and devices. And I will show you actually also the reason why this is necessary in many cases. And then I will tell you about grain boundaries. This is a topic I've started probably almost 20 years ago, and actually, learned more and more and added more and more results. And in the recent years, we really made, I think, strong progress in really understanding how grain boundaries affect the device performance of any device. So what I show you are results on solar cells that basically you can use these models on any semiconductor material and on the corresponding devices, right? Okay, let's go into detail and look at correlative electron microscopy. Okay, this is an example of a thin film solar cell. So what we look at is a cross-sectional specimen, and this is an EBSD, electron backscatter diffraction map, showing the local orientations in terms of false colors. Okay, and basically what you can do with this technique is to identify very nicely individual grains. Okay, so in this case, you have the impression, oh, this material is quite nice in terms of grain size, so it should be a good material, yes? I mean, it looks already nice from the grain size. But if you look at the elemental distribution, yes, there's indium and gallium, you can see that there is a depletion of gallium at the top of the layer, yes? So it's not so homogeneous anymore, what seems to be homogeneous, yes? And this actually you can corroborate by acquiring not energy dispersive X-ray spectroscopy. You can acquire also cathodoluminescence maps. This is basically, if you look at the distribution of the emission, the peak emission energy, you can actually see that there's a distribution of phases. Basically, the copper indium diselenide has a bandgap energy of round about 1 electron volt, and the copper gallium diselenide has a bandgap energy of about 1.7 electron volts, right? And so this is why from these emission energies you can deduce on a local gallium to indium ratio. And indeed you can see that this depletion actually here leads to a smaller bandgap energy at the top and a larger at the bottom. There's also an additional gradient, right? And all of a sudden, what seemed to be very homogeneous, yes, and nice, is a complete mess, yes, from the optoelectronic point of view. And that's actually what is of interest, because it's an optoelectronic device that we are operating. So the device is not so good, basically, because there's a lot of local variation in the bandgap, right? So you can also check the indium concentration, and you can see where there is less gallium, there is more indium, right? This fits exactly to what you can already deduce from these other results. And so basically, if you want to understand a material fully in terms of structure property relationships, you cannot rely only on one technique. You have to apply various techniques, and if possible, you have to apply these techniques on the identical position. Right? Then you can really fully account for structure, or in this case, microstructure property relationships. Okay, there are a number of results which I skipped because I think it makes the whole talk too long. But I have already collaborated with various colleagues working on Kelvin probe force microscopy or scanning tunneling microscopy, where actually we combine EBSD with scanning probe techniques. And so basically we can actually correlate local orientations or also grain boundary properties actually basically with structure, and then for example, the work function difference at grain boundaries, or in the case of STM, we can learn about the local density of states or of facets, and so basically can also detect density of defect states, yes, at certain facets and differences, and that's quite valuable information, yeah, for various material systems. And this work here actually gives details about combining EBSD with Raman microspectroscopy, and it shows that you can use Raman because the Raman intensity depends on the crystal orientation. Yes, and so you can use the Raman as a mapping tool to map local orientations of grains. This is quite interesting, and you can do that down to round about the diffraction limit of light, right? Round about 300, 400, 500 nanometers. It's quite interesting. And if you want to read about this in an overview, this is a review paper we have published 2 years ago, giving various examples and also some information about the specimen preparation that we use for these specimens. What I will concentrate on, as I told you, is on grain boundaries. And this is an example where I combined EBSD, electron backscatter diffraction, CL, cathodoluminescence, and electron beam induced current. This is basically the local short circuit current that you can measure when you use the electron beam as a light source, yes, to generate electron hole pairs. And if you apply these techniques on the identical positions, what you can see is that by means of EBSD, you can easily detect the local orientation of grains. You can detect individual grains, which means you can detect the grain boundaries, and you can also categorize grain boundaries. You can tell whether it's a high symmetric grain boundary, like a twin boundary, or a randomly oriented grain boundary. And you can see that I gave numbers, yes, and so basically there are more than 100 grain boundaries that I investigated. It was quite a work. I did that manually, yes, and then basically I looked at these various grain boundaries and I identified them in the other results, and basically was able to extract profiles across each and every of these grain boundaries to have some statistics, yes, so good statistics, more than 100 grain boundaries, and was able to determine the recombination velocity. This is something that we will concentrate on in this presentation. We need some way to quantify the recombination at grain boundaries, and this is done via the recombination velocity. Okay. So about grain boundaries, there are 2 publications, also recent ones that I can recommend. One is a review article about grain boundary in polycrystalline materials. This is for energy applications, but again, there are a number of details which are valid simply for each and every semiconductor. Right? There are also examples for battery materials or contact materials in various optoelectronic devices. And the second one is basically a publication which derives the equation for the recombination velocity, which we use to describe basically the recombination velocity as a function of various parameters. You will see this. I will show you in detail how this looks like. And also for band bending that occurs at grain boundaries. The band bending is essential because it's a kind of barrier for charge carriers. Yes, also this I will go into detail. And in this publication, we show applications of this model for various PV materials. Actually, I will also go into detail. You will see that you can actually apply this, this model on just any PV material that is currently relevant. And I think also you can, I have never done this, but if you took any other semiconductor, you can also apply this model for these semiconductors, I mean, provided that they are polycrystalline, of course. Okay, so let's say in a general comment, yes? I mean, if you ask yourself, what is actually the role, or what is actually the role of grain boundaries in a material and also correspondingly in a device where you use this material. I mean, a system, yes, any system, polycrystalline system, the lattice will always try to push anything that disturbs to the edges. Yes, that's what we do in our human societies. What we don't like, we push to the edges, yes, to the periphery, of the cities, okay? The grain does exactly the same, yeah? So anything in point defects, yes, impurities, anything that disturbs the lattice is pushed to the edges, which is why they segregate at grain boundaries or at surfaces. Yeah? And so what we find here is a higher density of defects, and correspondingly, we have enhanced non-radiative recombination of the charge carriers, okay, via the defects. So this is why you will never find benign grain boundaries, because in a way they're always detrimental, okay? Okay, so if we now look at the situation, again, this is segregation of, let's say, impurities, yes, point defects. Yeah? We have enhanced non-radiative recombination. This is one important detail of any grain boundary. Yeah? So you always have a higher density of defects that contribute to a higher rate of Shockley-Ritol recombination. This is a recombination describing recombination of excited charge carriers via defect states that basically capture the charge carriers, right, until they meet one another. So basically, if you have an excited electron and an excited hole in a semiconductor, they will at some point meet and then recombine, right? That's non-radiative because there's no emission of light. There's no luminescence emission. This is one important detail, and there's a second one. And this actually is linked to the fact that when we have defects at a grain boundary, they can exhibit a charge. It's not necessarily the case, but if you look at the ensemble of defects that are at grain boundaries, you have a certain excess charge, always. There's an excess charge density always present at each and every grain boundary, right? This means we have localized charges here. Now, if we look at a semiconductor, we know that there are free charge carriers, free electrons and free holes. And what do? They will redistribute. If you take a p-type semiconductor, we have an excess in holes. And the holes, of course, if you have a positively charged grain boundary, they would be repelled, yes, by the grain boundary. So there would be a depletion of free holes around the grain boundary, right? And correspondingly, if you have a negatively charged grain boundary, where the excess charge is negative, then of course it would be the holes would be attracted. So there would be an accumulation of free holes. And this redistribution, yes, translates via Bosum's equation to a certain distribution of the electrostatic potential, right? And if the electrostatic potential changes, we have basically a corresponding change of the band edges. And the band edges here, yes, you can see they form a barrier, which is a hole barrier if the band bending is downward, and is an electron barrier which when the band bending is upward. Okay? How much it goes up and down, we don't know yet. We will calculate this later. Okay? The important thing is that this mechanism with depletion and let's say accumulation of charge carriers, the redistribution only works, of course, if the net doping density is large enough. If the net doping density of the semiconductor is very, very small, we will never see a redistribution, and therefore there is no band bending. Okay? So we need a certain minimum net doping density to realize such a barrier. Otherwise, we don't have any. Okay? So you can already imagine that in order to fully understand this mechanism here in a material, we need to measure the net doping density. Okay? So, but now you understand we have two basically, details that actually contribute to the recombination, right? So one is the Shockley-Ritol recombination, which is enhanced at the grain boundary, and one is the barrier at the grain boundary, because what does the barrier do? The barrier would either repel charge carriers, yes, for holes here, or drive charge carriers towards the grain boundary. So it has a really strong effect on the recombination mechanism. Okay? When you look at measurements of recombination velocities, there is a publication by CEO and McDonald from the University of New South Wales in Australia, and they used photoluminescence mapping. So basically, you have photoluminescence intensity across a certain area. This is a microcrystalline silicon wafer, yes, and you can see the grain boundaries because you have enhanced non-radiative recombination at a grain boundary. So the luminescence, which is the radiative recombination, is reduced. And that's why the intensity in the photoluminescence is reduced. Okay? And they are able to simulate the profiles. When you extract them, they exhibit a certain decrease, right? And they are able to simulate it by simulating the PL intensity and the corresponding recombination mechanisms. And if they plot these recombination velocities, you can see that the values they measure, they go across various order of magnitude, yes? Yeah, from about 100, some 100 to some 10,000 times. And this is consistent, yes, for various types of wafers, P-type wafers, but also N-type wafers, yes, and also various treatments. Okay? So this is actually a starting point for me. Now I want to understand, okay, is this true only for silicon, or can we actually find this in other materials as well? So what we did was not to use photoluminescence, but to use cathodoluminescence, because then we are working in an electron microscope and our spatial resolution is smaller, which we need because the grain sizes in these materials that we look at are so small that we cannot apply photoluminescence. The resolution would not be sufficient. But the principle is exactly the same. What we do is this is a cross-sectional SEM image of a thin film solar cell. You have the back contact here, the front contact here, and this is the absorber, right? And in the absorber is polycrystalline, and you can see this quite nicely because in the cathodoluminescence intensity distribution, you see decreases wherever you have grain boundaries. What I don't show here is that on the same position, we acquired EBSD maps that confirm indeed, yes, we have grain boundaries exactly at these positions. Okay. Then what we do is to extract profiles across grain boundaries. They look like this, okay? And we can confirm by EBSD, yes, the position of the grain boundary is about where is the local minimum. Okay, this is as expected. And then what we do is not to look at the difference between the grain interior and the grain boundary in terms of the CL intensity, but we look at the logarithmic change. Because what we want to do is to obtain a linear function. A linear function showing basically how strongly does the intensity decrease towards the grain boundary. And how strongly it does decrease tells us something about the recombination velocity. This is the model, right? And in order to do so, what we have here is a reduced recombination velocity. This is the capital S. And the capital S actually consists of the real recombination velocity, yes, SGB, the bulk lifetime in the grains, which the lifetime of the charge carriers, and the effective diffusion length, which is used as a fit parameter for the linear function. To be a little bit more precise, the bulk lifetime can be measured by means of photoluminescence, but time-resolved photoluminescence. So we look at the transient, basically, how strongly the intensity decreases with time, right? This is the one of the established way to determine the lifetime. And we can then basically approximate this effective lifetime that we measure here as the inverse of this lifetime as the inverse, the sum of the inverses of the bulk lifetime and the grain boundary lifetime. So this actually is quite elegant because it gives us also an estimated value for the bulk lifetime, which is normally not so easy to determine. And then we put this bulk lifetime here into this equation. So then we have basically this equation, and this is the fit parameter, as I said. And so we have to successfully fit basically the linear function here. And then if we determine the recombination velocities, we have a median of all the values that you saw, yes? This we put in this equation. This gives us, if we know the average grain size, a second value basically for the grain boundary lifetime. And the idea is that these two lifetimes have to be the same. So we have to adjust this value here until these two are the same. Okay, so you have that iteratively to reach basically a good agreement. Let's say it's never really identical, but it's a good agreement. Yeah? Okay. So what we have to do in order to perform this model is to really take care of the injection level. Because the recombination is different when you have you generate more electron hole pairs by the electron beam than you have in terms of the net doping. So low injection means we're still in a position where the generated electron hole pairs, the density is smaller than the net doping, right? Otherwise it would be higher. And you can detect a transition normally by a very strong increase in the CL intensity. Why is this? It's because the CL intensity is radiative recombination. That's what we see. It's a radiative recombination rate. So the higher the recombination rate, the higher is the CL intensity. Yeah? And if you reach the point where the generated electron hole pairs are equal to the net doping, the number of electrons and holes are the same. So you don't have majority and minority charge carriers anymore. In this case, the recombination rate is maximum because the recombination rate is proportional to the product of electron and hole concentrations. Okay? So this is why it's a kind of, it's not exactly an abrupt transition. It's still, it has basically, it's a bit retarded, but nevertheless, you can see this if you go, if you vary the current of the electron beam, yeah, you can see that very nicely that there's a transition. Okay, so this is actually the reason why we see this transition. And yeah, it's gradual actually. The change is gradual and not abrupt, right? And so we can actually, what we can do actually is to estimate, yes, where actually we have to remain with the current in order to remain in low injection conditions. This is, and if you look now at what happens at the grain boundary, is exactly a consequence of what I explained to you. As long as we are in low injection condition, we have in the grain interiors a certain level for the luminescence intensity, right? And then there's a decrease to the grain boundary because of higher Shockley-Retaux recombination at the position of the grain boundary. But if we go to high injection conditions, there is all of a sudden a very high luminescence intensity. And the decrease is much, much stronger. You can see this. What we did is simply to vary the current as for a specific material. This is a small current, yes. This is not a very strong decrease. But if you go to high current, then all of a sudden you have a much higher decrease, and so a much higher recombination velocity, which is not present if you operate a device in low injection conditions, which we normally do, right? So if we use a material like silicon, cadmium telluride, copper indium gallium diarsenide, all of the established materials for photovoltaics, we would always have low injection conditions. And this is why one has to be extremely careful finding the right parameters for the measurement. Okay, so but if we do that, such measurements on various material systems, I gave you the results here for silicon. These are just examples, not representations for these technologies, okay? But I took out some of the cells which we investigated, right, and various technologies. It's very interesting. Look, there's a very similar behavior. Always a distribution across several orders of magnitude. Okay? For halide perovskites, I will come back to this case. It's a very small median value, yes? But the others, they remain more or less on the order of maybe several 10 or several hundred or maybe several thousand centimeters per second, right? But always the same behavior. And if you say, okay, this is quite nice, but it's not a very good statistics, this is what we have measured so far. And we have measured actually a few more, yes? So what you look at is at about 30 different measurements, yes? All the axes are all the same. They go from 0.1 to 20,000, okay? And you can see that the behavior for all these samples here, this is copper indium gallium diselenide, this is microcrystalline silicon, this is halide perovskite, this is casterite material also used for solar cells, this is cadmium telluride. You see the behavior is always the same, goes over several orders of magnitude, right? And this calls, of course, for a common model, right? It's quite evident that something must be very similar for all these cases if the recombination velocity always behaves quite similar. So what actually is behind this? And when I will show you the model in a moment, but when we discussed with a collaboration partner, so one actually colleague said, but you know, the grain boundary actually is not oriented like this, right? There can be various, we see some line, yes, in our cross-section, but how is it oriented in this? Do we know? How we cannot detect, right? So maybe what we see is only an effect of the geometry, yes, of the grain boundary. So of course it means that we have to simulate profiles. And yes, of course, there is a strong effect on the inclination angle on the grain boundary profile, yes. But what we can determine is that, and confirm, is that there is no effect on the recombination velocity of the inclination angle. The recombination velocity is completely independent of the inclination angle, completely. So this is not an issue. Instead, what we can come up with, and this is actually detailed in this publication, is that the recombination velocity can be described by two factors, by two parameters. One is a prefactor that contains the Shockley-Rayleigh recombination. It's a recombination velocity only taken care of in how far do the defects at the grain boundary contribute to enhance Shockley-Rayleigh recombination. Okay? This parameter here in the exponential function is the barrier height. Yes, the barrier height that we actually calculate from the redistribution of charge carriers, free charge carriers. Okay, so there are two parameters actually, and also in the publication we can we derive basically these equations here for upward and downward band bending. I mean, this one here is already known in the literature, but I was quite astonished that there's absolutely no publication about the upward band bending. So the barrier for the minority charge carriers. This has never been dealt with, really, because it's a quite nasty derivation, I can tell you. It's not so nice. This is a 4 or 5 liner, very easy, yes? You can find it in many, many publications. And the interesting thing also is that what you see when you derive this equation is that by the derivation itself, this magnitude is limited. It means that the barrier heights are maximum several tenths of millectron volts, either upward or downward. So it's a very small perturbation of the conduction or valence band edges. Yes, very small. This means also that the current is not very affected. So the transport of charge carriers is not affected. But we have an effect of the recombination because this magnitude here is changed quite drastically by the exponential function, right? So we can imagine a very small change in this barrier height already invokes a very large change in the recombination velocity. And this makes the large range of recombination velocity values that we can find for each and every technique, yes, each and every material system here. Yeah? The fact that we find such a behavior is because of the exponential function. Okay. Right? Okay. And what we can now do is to say, okay, we measure recombination velocities. Let's see whether we can find appropriate values for the prefactor, right? And also for the excess charge density, which is one parameter here describing the barrier height, right? If we know, of course, if we have a certain temperature, absolute temperature, and a certain doping density and dielectric permeability, right, of the material, we only need basically the excess charge density that we can vary. And you understand immediately, okay, we have two unknowns for one measured quantity. Of course, we cannot determine these quantities here very precisely, right? But we can give ranges, yes? And this is only one example here of a measured data set, yes, for one of these samples that you saw. You can see that basically the corresponding ranges are in blue for downward band bending and in red for upward band bending, yes, given for various values here. And in some cases, you cannot tell whether it's downward or upward band bending. Yeah? In some cases, it can be both. Right? But you can find corresponding ranges for the prefactor and for the excess charge density, which means that you have a corresponding range for the barrier height. Right? Okay. This is better than nothing and is an important input for device simulations. I will show you at the end of the talk. Right? So for halide perovskites, we saw that basically the values were very small. And the range is also, let's say, confined to 2 orders of magnitude, roughly. This is because in this specific case, the doping density is very, very small. So it's so small that there is absolutely no redistribution of free charge carriers because there are no free charge carriers for this redistribution, so there is no band bending. Okay? And the equation changes to this form. Okay? So we have here the density of defects that make the Shockley-Retaux recombination, the corresponding capture cross-sections for holes and electrons, and the thermal velocity, which we assume to be equal for electrons and holes. And altogether, it gives, again, a kind of prefactor which slightly varies, yes, from grain boundary to grain boundary. This is the picture. And these defect densities are very small because the doping density is very small. So we can also give some estimations for these values. But this is basically the reason why in this specific material we have a very special behavior. Okay? So now what we have seen is everything about the recombination velocities. We have seen also behaviors in various materials, and we saw that the model can describe all of these results. Right? Now what we want to see, okay, what is now the impact on the device performance? And basically, I can give you this on one slide only. Okay? So let's see. We have here our equation for the recombination velocity. Okay? Then we have the equation that you already saw for the lifetime at the grain boundary. Right? We have an average grain size. We have the median value of all these values that we measure of the recombination velocities in the material. Right? So how can we proceed? We know that we can describe the effective lifetime as a contribution of lifetime in the bulk. And if we have now a complete device, we have a bulk lifetime, we have grain boundary lifetime, but we have, of course, also lifetime at the interfaces, right? And we can actually sum them, the inverse of this lifetime up to get the inverse of the effective lifetime, right? That's quite convenient. Now, the next step is to find an equation for a parameter in a photovoltaic cell, and this is the voltage. To be more precise, it's the open circuit voltage, VOC. If we want to describe the VOC, we can see the VOC is indeed a function of the effective lifetime, right? We have some other parameters. This is the ideality factor, the Boltzmann term. Okay, it contains the absolute temperature. elemental charge, and then we have the generation rate, so the generation rate of the light that impinges on the solar cell and generates electron hole pairs, and we have the electron concentration on the p-type side of the solar cell in unilluminated condition in thermodynamic equilibrium. So basically, and this can be determined, but actually in order to really assess what the effect on the grain boundary recombination on the VOC is, or to calculate the losses, what we can do is to look at the situation with and without grain boundaries, and then we can see that basically for this term here, we can just put in this magnitude or this equation, right? And if we look at differences, basically the ln of differences, or the ln of a term minus the ln is basically nothing else than the ln of term 1 divided by term 2. And this actually gets rid of the GL and this electron concentration, and we only have lifetimes. And then what we can do is we actually can end up with this equation. Yes, and you can see it only contains the lifetimes in this equation. For convenience, I took one term for both interface lifetimes. Okay, so and then what we can do is to use photoluminescence quantum yield measurements. So actually we can determine this quantity by looking at the emitted photons from a material divided by the number of absorbed photons in a material, right? And this is done by photoluminescence measurements, standard technique. And actually, if you put this in this equation here, you can calculate the total loss of non-radiative recombination of an open circuit voltage, right? And that's the upper limit, basically, of the open circuit voltage loss of what you have at grain boundaries. And this actually gives you means to discuss the impact of the grain boundaries or the grain boundary lifetime, yes, with respect to bulk lifetime and the interface lifetime, right? That's means basically it gives you a range basically of these lifetimes, and you can actually discuss that or find that the VOC loss by recombination at grain boundaries is at least a few tens of millivolts, even for the best solar cells. Yes, but of course always reaches a certain maximum that depends on the photoluminescence quantum yield of the material. Of course, it's good to do this in this way, and it's a nice way actually to calculate, but we have, of course, tools to really simulate the device performance, and this is actually two-dimensional device simulations that we can use, for example, for using Centaurus software, sorry. And what the colleagues in the University of Halle in Germany did, they took a grain boundary grid extracted from an EBSD map as a basis for the calculation of the device simulation. And this is quite nice because then you can really use the real microstructure as a basis, and not just some arbitrary grid that you can think about. It's a real grain boundary grid that is extracted from an EBSD map. And then what you can do is to vary exactly the excess charge density and the prefactor, yes, that we have from our evaluation of the CL measurements, in order to see, okay, how do these parameters affect the device performance. And we did that back in 2020. But here what we did was to use just two values for the downward and for the upward band bending, right? So just two extreme values. And then we varied the prefactor. So the prefactor was varied between 0 and 1000. And these are the experimental values for the open circuit voltage, for the current, short circuit current density, fill factor, and the efficiency of the solar cell. What you can see is what I already told you, because the band bending values are so small, the current is hardly affected. It remains almost the same. There's hardly any effect on the transport. But there's a strong impact on the open circuit voltage, right? And it fits to what we actually predicted. It's a few tenths of milli-electron volts, yes, when you assume a certain recombination velocity range. In this case here, there's a good agreement what we find here. And in these measurements of CL, we find a median value of a few hundred centimeters per second that agree very well with the order of magnitude that we can estimate here. Right? There is some discrepancy here between the fill factor values and the simulated ones and the experimental ones, but this is because the model was not so perfect in terms of the contacts. Right? So this is also why here we have some deviation. Okay? So you can see there's a confirmation here, but when we actually ended this project, we said, what actually is true in 2 dimensions must not be true in 3 dimensions, because we look at a 3-dimensional object, right? And we cannot assess the microstructure in 3 dimensions here. So it means that we can also not assess the impact of grain boundaries in the real solar cell. So, of course, we have to get 3-dimensional EBSD data as a basis for a 3-dimensional device simulation, right? And that's the first time in the literature. I think there's no other example where a real microstructure was used as a basis for a 3-dimensional device simulation. And basically, we get a confirmation of the results that we get from the 2-dimensional device simulations. There's a slight underestimation of the impact of grain boundaries on the VOC loss by the 2-dimensional simulation. It's simply a geometrical issue. I mean, you cannot not by just assuming, oh yes, more or less, you can rely on one section that you look at. It's simply not getting close to the real world that we can actually find here. Okay, so conclusions. Yeah, we saw recombination at grain boundaries. I showed you examples from semiconductors used for photovoltaic absorbers, but we can actually apply this model to just each and every semiconductor. It's a simple model. Yes, it has 2 parameters, a very short form, and there are always 2 contributions: the Shockley-Ritor recombination of the prefactor, yes, and band bending that actually is contained in the exponential function. And the device simulation, device limitation is mainly via the voltage of the device. And voltage losses, there are up, several tenths of millivolts up to more than 100 millivolts, depending on the material system. Thank you very much. Muito obrigado. Porque tem gente assistindo, né? Tem?
Hi, Daniel. These solar cells you showed us, these are the 6 solar cells, right? SIGS.
Yes, CIGS.
Yes. The fill factor and the GIC are okay, but your VOC is quite low. Is it typical of this kind of solar cells, or?
Yes, even for silicon, it's not so large. Yeah, because the bandgap energy is low. It's 1.1, 1.15, and so the current is at the Shockley-Weiser limit, it would be 900 millivolts.
Yeah, so is it typical from your results, or is it possible to get a higher VOC in the literature for this kind of system?
No, I mean, basically, even the best solar cells, they have voltages of yeah, maybe 770 or 780 millivolts, but not more than that.
Okay. And these solar cells, they are already commercial?
Yeah. No, of course. I mean, nowadays it's difficult, right? Because the market is quite dominated by crystalline, single crystalline silicon, right? I mean, about 97–98% of all the market. But there were other times, and basically there were also big companies, also big productions, going up to, I think, 1.5 gigawatt per year, which is quite substantial. A lot of modules realized by Solar Frontier in Japan. The market is as it is, and it's difficult to maintain a large scale production, right? If the market actually develops in such a direction, right? So, but yes, these are highly established technologies.
And I mean, if you want to compete with silicon, they have to have something which is better than silicon. Are they cheaper? Are they easier to produce?
Yes, exactly. So basically, I mean, there are various issues. So first of all, it's a thin film technique, which means that you can deposit it on just any substrate, right? And many of the companies that existed and don't exist anymore, they used a roll-to-roll production. Very nice. So basically, you have a substrate, you put it into the machine, and what comes out of the machine is the complete solar cell that you can roll up, yeah, for the transport wherever you like to use it. You can use, of course, such solar cells of any kind of shape, roof, yes, and also, what was or is still an issue is to use them as in a facet, as a building integrated photovoltaic, yes, because the color of these solar cells is very nice. It's very black, yes, and architects like it to include them into any kinds of buildings, also huge buildings, right? I mean, to really decorate the whole facet with solar cells. These are not dreams or projects to come. These are already real. I mean, you can find such buildings all over the world.
Okay, thank you.
Again? Anyone else? This slide, when you make the experiment, you make the experiment with an actual system, 3D system. And when you make the comparison with the 2D system, how is it reasonable?
I mean, normally what you do is to look. I can use the same grain boundary parameters, for example, for the recombination, and I look at how well the experimental PV parameters can be simulated. Right? We don't change anything else, the material. We only change the dimension, basically, of the model. And then we can see how well can I get close, basically, to the PV parameters that actually measure on the solar cell. And yeah, basically, this is the bottom line. And you have, of course, you saw, of course, also that there is this large variation in the recombination velocity. Then you can see how strongly actually it changes, basically, right? And in how far, because what you have in the end is, of course, individual contributions of these recombination velocities on a macroscopic quantity as the open circuit voltage, right? And there is an impact on the of the dimension. I mean, there is an impact on the device performance of the dimension that you use. You can simply not so easily simulate the experiment when you use 2 dimensions.
Please, can you comment on the effect of the dimensionality, in the sense of you bring us in the end of the talk the 2D and the 3D models? Those are based
acoustically. I'm sorry, I have problems to hear you. Can you put it a little bit?
Sure. Yeah. Can you comment on the effect of dimensionality, the sense of you bring us in the end of the talk, the comparison between the 2D and the 3D models. So the 3D models, the basis is the same. I mean, basically here, you are only implying the geometry if you need to improve your model somehow, because the message that I understood, that basically you recover the 2D and this is it. Am I right? Or?
Yeah, so, I mean, okay, so for example, when you want to assess the microstructure, right? I mean, what you do in 2D is you have a section through grains, and you look at certain diameters, or you can see basically how large the distance is between individual grain boundaries, right? And then if you do that in 3D, it's a completely different story, because in one direction the distance is short, but the other is large, right? And so there are these geometrical issues that sum up and in the end lead to, I mean, it's not a bad result. Yes, it's not a bad result, but it's not as precise as the 3D case. And the 3D case here, I forgot to tell you, was actually applied to 5 different cells, so not just the one cell. And so it can be seen quite easily when comparing 2D and 3D for all 5 cases. 2D is okay, yes, and it's already better than having an arbitrary grid, yes. That there's some very funny papers, yes, showing only grain boundaries going from top to bottom, or grain boundaries like this, or even one case it's only like this, yes, or so. But it's simply this limitation.
Just one more question. You mentioned that you did somehow, I didn't get it exactly how, you got a 3D image. It's a real 3D image, or you just took a small cube and you look at each face of the cube?
This one here?
Yeah.
No, this is actually calculated or extracted from such a data set.
Okay.
It's simply, okay. I mean, when you look at it, you think, it's strange, right? Because it looks a bit, let's say, cut off and things like that. But this is just, the reason is just because you have to limit the size, yes, of your cell somehow, right?
Ah, okay.
And then you have to use a certain section from your map.
But
you cannot.
What technique did you use to get this left image here?
This one here is a 3D BSD measurement.
So it's possible to do it really in 3 dimensions. It's not a trick you are using, it's not a kind of tomography.
Exactly. So basically, it's a sequential process where I measure EBSD on a surface, and then I use a FIB instrument, right, a focused ion beam machine, to slice a very thin slice of 50 nanometers away, and then I acquire another EBSD map. Okay. And then another slice, another, and so on, and the stack can be reconstructed to actually result in a 3-dimensional data cube.
Okay, great, thank you.
But this is established, it's not our invention. I mean,
Então vamos agradecer, né, speaker. Thank you very much.
Muito obrigado.